Okay, so we're going to talk today about the mean value theorem, which is related very much to a theorem called Rolle's theorem. And then we'll talk about what you can do with the mean value theorem and why I think it's so important. So first, let's talk about the Rolle's theorem. Rolle's theorem is based on a very simple idea. And to picture that idea, let's all pretend that we are cyclists, right? We're riding in the Tour de NYU. And we're going up and down these hills. Okay, our campus is not that hilly. But if we were in a bike race, we'd be going up and down hills. And if you consider at one point in the bike race you're going uphill, and another point in the bike race you're at the same elevation but going downhill, then at some place in between, going uphill and downhill, you reach the top of the hill. Okay, that's what Rolle's theorem says. Rolle's theorem says if you bike upwards and then downwards, at some point your elevation was stationary. Okay. Now what does that all mean mathematically? We can think about the elevation function over time as representing how high above sea level you are as you're biking. Okay, and that's just another example of a function. So Rolle's theorem says that if you have a continuous function defined on a closed interval a to b, which is also differentiable on the open interval inside that closed interval, the open interval a to b, and satisfies the condition that the function value at a is equal to the function value at b, then there is a point, we'll call that point c, in between a and b where the derivative at c is equal to 0. Okay, so here's a sample. We've got a function like that. F of a and f of b are both 0 in this case. It's not required, but they are equal. And in between them, we see that there's a point where the derivative is 0. We can see that the derivative is 0 by drawing the tangent line and noting that it's horizontal. Okay, so all Rolle's theorem says is that any function that you can think of, which is continuous on a closed bounded interval and differentiable on the open interval inside, has the same function values at the endpoints, will have to have a stationary point in the middle. Now, not exactly in the middle. In this case, it did end up exactly in the middle, but somewhere in the middle. Okay, that's Monsieur Rolle's theorem. And here's my flowchart proof of that theorem. We use the flowchart to show how the closed interval method works, and I thought it would help here as well for proving Rolle's theorem. So what we want to do is we've got a function that satisfies these properties. We want to show that there's a stationary point inside the interval. Well, what I'm going to do is take the maximum point. This function is a continuous function on a closed bounded interval. And so by the extreme value theorem that we talked about on Monday, there must be a place where it achieves its maximum value. Okay, we know that exists by the extreme value theorem. And it's either an endpoint of the interval a to b or it's not, right? One or the other. If it is an endpoint, well, we'll think about that in a second. But if it's not an endpoint, then it's an interior point. That means it's a local maximum. And then by Fermat's theorem, the derivative has to be 0. It has to be differentiable because we said it's differentiable all over that interval a to b. So lo and behold, if the maximum point is inside the interval a to b, that is the place where the derivative is 0. And that's what happened here. The derivative was 0 at the maximum. Now, we might be unlucky, at least unlucky in this case, and find that the maximum is achieved not inside the interval, but at an endpoint of the interval. And if that's the case, let's just look at the minimum instead. We'll call the minimum d. Same question for the minimum as we asked for the maximum. Maybe it's an endpoint, maybe it's not. If it's not an endpoint, then it's an interior point. And again, by Fermat's theorem, we would be able to conclude that the derivative at d were equal to 0. So if the maximum's inside the interval, bingo, place with a stationary point. If the minimum is inside the interval, bingo, another stationary point. If we are so unlucky as to have neither the maximum nor the minimum inside, that is, both maximum and minimum are endpoints, then what kind of function is this? Well, it's a function where the value at one endpoint is equal to the value at the other endpoint. One of these values is the maximum, and one of them is the minimum. But those are the same. How can a function have its maximum equal to its minimum? The only way that can happen is if it's a constant function. And if it's a constant function, I can take any point inside the interval a to b. The derivative there will be 0. Okay? So if you look in the universe of functions, 99% of them will have their maxima inside the interval that they're defined. And then among the 1% that don't have that property, 99% of those will have their minimums inside. And so, you know, this takes care of 99% times 99% of the cases. But in the 1% of 1%, where the endpoints are on the maximum and the minimum, we still get a place where the derivative is 0. So any way you consider it, no matter what case you're in, you're going to find stationary points of the function. All right, well, great. So that's true no matter what kind of function you have, but it has this sort of condition that seems a little bit tedious, that the values at the two endpoints have to be the same. If we look back at the functions that we were investigating in the last class, not many of them had that property that f of the one side was equal to f of the other side. So the mean value theorem is a way to get around that assumption. We get a different conclusion, but the theorems are very closely related. The heuristic idea behind the mean value theorem works something like this. If we are driving now, we've switched from the bike to the car, and we're going to drive between, say, New York and Philadelphia. How far away is Philadelphia? Let's say it's, I don't know, 150 miles? Okay. If we drive and we leave at noon and we arrive at 3, what's our average speed? 150 miles, took us 3 hours to get there, 50 miles an hour. The mean value theorem says that at some point on our trip, the speedometer read 50 miles an hour. Okay? And this seems pretty reasonable, because if at all points our speed was less than 50 miles an hour, we probably wouldn't be able to average 50 miles an hour. And if all times our speed were greater than 50 miles an hour, well, first of all, we've got a supercar because it starts at something greater than 55 miles an hour. And second of all, we would get there faster than 3 hours. Okay, that's the idea behind the mean value theorem. Mathematically, again, we could think about f as the position function over time, but you can say it for any kind of function, but the conditions are still going to be the same. It has to be continuous on a closed interval a to b, and differentiable on the open interval inside that closed interval. The conclusion is a little bit different, because we've now relaxed the condition that f of a and f of b were the same. Instead, what we say is that there's a point, we'll call that point C, in between a and b, such that this quotient here, f of b minus f of a over b minus a, is equal to f prime at C. Okay. So what in the world does this mean, and how is it related to Rolle's theorem? Well, geometrically, what does f of b minus f of a over b minus a represent? Slope of what? Slope of the tangent line? Okay, well, there's lots of tangent lines, so slope of the tangent line at the point AB? No, because A and B are different x's, right? Here's A, here's B. There's no point AB. F of B minus F of A over B minus A represents the slope of what? The tangent line on the curve at any point C? No? Yes? Yes, yes, it's the slope of the secant line that goes through f of b minus, goes through the point a comma f of a and b comma f of b. There it is right there. That's the secant line. F of b minus f of a over b minus a is the change in y divided by the change in x between those 2 points. Now f prime at C, what is that the slope of? That is the slope of the tangent line to the curve at C, and there is that. Now you said any point C, and it's not true that this slope is the same as the slope of the tangent line at any point C, such as this one here, or this one here. Okay? But there is at least one point in the interval a to b where the slope of this tangent secant line equals the slope of that tangent line. There's some point inside where the average rate of change over the entire interval is equal to the instantaneous rate of change at the point C. Okay, and that's what's so special about C. Okay, so how is this related to Rolle's theorem? For Rolle's theorem, we had this extra assumption that f of a were equal to f of b. And the extra conclusion was that there was a place where the derivative was exactly equal to 0. And if you were to have f of b equal to f of a in the mean value theorem, then you would get the same conclusion. You would get that there's a point C for which f prime of C were equal to 0, right? If f of a and f of b are the same, this difference quotient is 0. Okay? But how were they related? Well, 0 is the average rate of change over this interval in the first picture, and it's the instantaneous rate of change at the point C. The average rate of change is not 0 here, it's some difference quotient, but it's still equal to the instantaneous rate of change at the point C. So the difference between Rolle's theorem and mean value theorem is really just a question of perspective. If my x-axis were not going this direction, but instead we're going through the points A and B, or the point A comma f of A and the point B comma f of B, then you would have the same conclusion, and that's that the tangent line is parallel to the axis. Right? Tangent line is parallel to the secant line. That's the big idea. Okay? So far I've been drawing just a bunch of pictures, and everything here is very intuitive. Rolle's theorem we proved with a flow chart. I'll prove the mean value theorem using a different function. Okay, so if, like I said, if you change the x-axis to be not this horizontal line, but this diagonal line that goes through A comma f of A and B comma f of B, then you have very much the same picture. What that means is that we can apply Rolle's theorem to some tweaking of this function f in order to create a function which has the properties we need. So the line that goes through these points, A comma f of A and B comma f of B, we know what its slope is. It's f of B minus f of A over B minus A. And we know that it goes through the point A comma f of A. So if you do point slope formula on that information, what you get is that the equation for this secant line is f of A, y equals f of A plus f of B minus f of A over B minus A times x minus A. Right? Very much like the linear approximation to a function near a point, except we're not approximating with the tangent line, we're using a secant line. So what I will do is take my function f and subtract from it the equation for the secant line. So f of x minus L of x. And if I look at the equation for L of x up here, what I'm doing is subtracting f of x minus f of A minus f of B minus f of A over B minus A times x minus A. Okay. That's a big equation to put all at once. That's why I put this intermediate step. Okay. This represents the difference between f of x and the secant line. Okay. Sorry. Whoops. Now, g is a nice continuous function because f's a nice continuous function. L is a straight line, as continuous as you want. Also, f is nice and differentiable inside a to b. L is nice and differentiable inside a to b. So their difference will also be as differentiable as you like. Now, what is g of a? What do I get when I plug in a to g? Well, follow it through with me. G of a is f of a minus L of a, or f of a minus f of a minus f of b minus f of a over b minus a times a minus a. What is that? That is 0, right? F of a minus f of a is 0, a minus a is 0, and so I just get 0. So g of a is 0. And what is g of b? G of b would be f of b minus L of b, or f of b minus f of a minus f of b minus f of a over b minus a times b minus a. And what's that? That's also 0 because it reduces to f of b minus f of a minus f of b minus f of a. Okay? So g of a is 0 and g of b is 0 as well. So what we've done is we've created a new function which is continuous on a to b, differentiable on a to b, and has g of a equal to g of b, so we can use Rolle's theorem on g. So Rolle's theorem says there is a point C in between a to b for which g prime of c is equal to 0. Now, if you look at what g prime is f prime minus L prime. And what's the derivative of a linear function? Just the slope. Okay? So to say that g prime is equal to 0 is the same as saying f prime equals L prime, or f prime at c equals the slope of the secant line. Okay, so there you have it. Rolle's theorem and the mean value theorem are actually equivalent because you can use Rolle's theorem to prove the mean value theorem, and you can use the mean value theorem to prove Rolle's theorem. But mean value theorem is a little bit more flexible because it has fewer assumptions to it. It'll apply for any function, not just the ones that have their values equal to each other on the endpoints. Okay. So what can we use the mean value theorem for? Here's a nice little sample problem. Show that there is a unique solution to the equation x cubed minus x equals 100 in the interval 4 to 5. Okay, so put your mind back in the let's see, I guess in the chapter 1 sense. And we talked about solving equations like this, x cubed minus x equals 100. What might be an important theorem that you would use to say that this equation has a solution? The intermediate value theorem, and that would apply to which function? Intermediate value theorem is a theorem about a function, so continuous functions. And in this context, which function? Okay, x cubed minus x equals 100 is an equation, though. Where's the function? Okay, so you can apply the intermediate value theorem to the function x cubed minus x minus 100 and show that it takes the value 0. Or you can apply it to the function x cubed minus x and show that it takes the value 100. Either way, you will apply it on the interval 4 to 5, plug in 4, plug in 5. In one endpoint, you'll find something less than the value you want. On the other endpoint, you'll find something greater than the value you want. And so you can use the intermediate value theorem to say that there has to be a point in between where it does take the exact value. Okay? So here I applied it to the function x cubed minus x. If you plug in x equals 4, then you get 64 minus 4, 60. If you plug in x equals 5, you get 125 minus 5, 120. And the 100 is in between 60 and 120, so it has to take the value somewhere. But the question is, why is that point going to be unique? How do I know that there are not two solutions to this equation? Okay, and this is where we can use our new information. If there are 2 points in between 4 and 5, with f of the first point and f of the second point equal to 100, then I can use Rolle's theorem, or the mean value theorem, to show that in between them there has to be a point where the derivative is 0. So f of c1 is 100. If there's another f of c2, which is 100, then in between c1 and c2 there's got to be a point, I'll call it c3 because I'm running out of letters, for which the derivative is equal to 0. Okay? Now, what does that mean? I can find the derivative of this function. It's 3x squared minus 1. And if I look at 3x squared minus 1 on the interval 4 to 5, what I'll find is that, let's see, f prime of 4 is 47, and f prime of 5 is 74. The derivative is positive all over the interval 4 to 5. There is no place in the interval 4 to 5 where f prime at that point is equal to 0. Okay? But I just said that there had to be a point in between c1 and c2. c1 and c2 are both in between 4 and 5, where the derivative is 0. So these things both can't be true. And the thing which is not true has to be this one. It's impossible to have 2 different points where the function takes the value 100. It would contradict this thing that we know is true. Okay? So that's an example of what we call in the math business proof by contradiction. If you want to show that something is true, you might be able to do it by assuming it's false and then deriving something which contradicts known facts. So there we have it. We've shown that there is a unique solution. There's only one solution to this equation, x cubed minus x equals 100, in the interval 4 to 5. Okay? Now, it doesn't say where it is, but it says that there is one and that there's only one. Questions about that? Okay. So here's another little use of the mean value theorem. We can use it to estimate values of functions. One thing we know is that the sine function has a range in the interval -1 to 1. So we could say it in this way, that the absolute value of the sine function is less than or equal to 1, no matter what x is. One other thing we've learned, using linear approximation, is that sine of x is approximately equal to x for small x's. Right? We did that using the derivative of the sine function at 1. At 0 is 1, so the linear approximation is just the line y equals x. What we'll show now is that the absolute value of the sine function is less than or equal to the absolute value of x for all x, which is kind of useful because it's not just approximate. We know in which direction it's an inequality. So the sine of 0.1 is less than or equal to 0.1, and not just approximately 0.1. Okay, so that's why we would want to do something like that. And here is how you would do it. Let's look at the function sine on the interval 0 to x. Okay, so I'm going to say something about sine x x is fixed. So if I'm talking about the function sine, I can't call it sine x anymore. X is already used, so I'll just call it sine of t, just to use another variable name. So what we get using the mean value theorem is that f of x minus f of 0 over x minus 0 has to be equal to f prime of some point c in between 0 and x. Okay? Now, f of x is sine of x, and f of 0 is sine of 0, and sine of 0 is 0. Divide that by x minus 0. That's the same thing as sine of x divided by x. And f prime is cosine. So to say that f of x, b minus f of a over b minus a is equal to f prime of c, in this case, is saying that sine of x over x equals cosine of c. Okay, now what do we know about c? Not too much, except that it's in between 0 and x, and we know less about x. However, we do know that the absolute value of the cosine of c is less than or equal to 1. And you can use that to say that the absolute value of sine x divided by x, that would be equal to the absolute value of the cosine of c. That has to be less than or equal to 1. And so sine x over x's absolute value has to be less than or equal to 1. All right, now sine x over x absolute value is like the absolute value of sine x divided by the absolute value of x. And you can multiply both sides of this inequality by the absolute value of x, and you get sine x is less than or equal to x in absolute value. So you can use the mean value theorem to estimate values of functions, and not just approximate, but in terms of strict inequalities. So back in the day, I did a little research program at Indiana University, woohoo, and I had to prove something about differential equations. We talked a little bit about differential equations. I had to show that the solutions to this were stable, and so it amounted to estimating the difference in a function's value and what it would be if we had assumed other conditions. And it was all estimations, and I went to my advisor and said, I don't know how to do this. And he said, oh, it's just the mean value theorem. And sure enough, I wrote a paper. It was like a 20-page paper, and on 15 of the pages, I wrote, by the mean value theorem, this is true. By the mean value theorem, this is true. Because you can use it to estimate values of functions. Okay. Here's another estimation problem using the mean value theorem. Let f be a differentiable function, and I don't know lots about it, but I do know that f of 1 is 3. And I do know that f prime of x is less than 2 for all x in the interval 0 to 5. And the question I want to ask is, could f of 4 be greater than or equal to 9? Okay, differentiable function. I don't have its equation. All I know is these things. It's differentiable. F of 1 is 3, and f prime is less than 2. What can I say about f of 4? Well, what I need to do is relate the information I know about f of 1 and f prime of x to f of 4. So I can look at the difference quotients, f of 4 minus f of 1 over 4 minus 1. That's equal to some derivative, f prime, at some point c. And we know that the derivative is bounded above by 2. Okay? Now, like I said, I don't know too much, but I do know that the derivative is less than 2, and using the mean value theorem, I can make this inequality. Solve that inequality for f of 4, and what you get is that f of 4 is equal to f of 1 plus f prime of c times 3. That looks like a linear approximation, right? But it's actually an equality when you use the mean value theorem. That would be less than, well, f of 1 is 3, f prime of c is less than 2, and 3 is 3. All right, so a chain is only as strong as its weakest link. We have less than here, so when we interchange everything for what we know it's equal to, we still have less than. What we get is that, reading it from left to right, f of 4 is less than 9. Okay, now, so it's not possible that f of 4 is greater than or equal to 9. In fact, just the opposite, f of 4 has to be less than 9. Here's the picture of what's going on. We have the function. All we know is that its derivative is less than 2. And here's the function whose derivative is exactly 2. That is the straight line that goes through 1, 3 with slope 2. Okay, and what we see is that f of 4 ends up being less than that line followed all the way through to 4, which would be 9. Okay? This is sometimes known as the racetrack principle. You know I like colorful metaphors. The racetrack principle says that if you have two horses which start at the same time, but one horse always runs faster than the other, then the faster horse will always be ahead of the slower horse. Right? Goes without saying, seemingly so, but it's equivalent to the mean value theorem. Here's our faster horse. It's running at a speed of 2. Here's our slower horse, which is running at a speed of something less than 2. And no matter what points we look at, the faster horse is always going to be ahead of the slower horse. Okay? So this is how deep the mean value theorem goes. Okay. Here's another interesting question. Food for thought. Driver travels along the New Jersey Turnpike. Where are my Jersey boys at? And girls. Okay. So you know about the New Jersey Turnpike. And you know that they use a system called E-ZPass to count tolls. Now, E-ZPass has since conquered the world. It's not just the New Jersey Turnpike, but it's on the New York Thruway. It's on the Pennsylvania Turnpike. You can even use it on the Ohio Turnpike. Eventually, you'll be able to use it from coast to coast. Soon, all things will be E-ZPass. Now, what does E-ZPass do? Instead of paying an actual toll with money, or with coins, with cash, you have a transponder in your car. And when you drive onto an E-ZPass controlled freeway, it records the time and the position when you get on. And then when you get off the turnpike, it also records the time and the position that you get off. And based on the distance you have traveled on the turnpike, it deducts a certain amount of money you have from your E-ZPass account. So that's what this driver does. The system takes note of the time and place. The driver enters and exits the turnpike. A week after his trip, the driver gets a speeding ticket in the mail. Now, how could this be? Which of the following best describes this situation? Is it A, E-ZPass cannot prove the driver was speeding and is just trying to extort some money out of the driver? Is it B, E-ZPass can prove that the driver was speeding? Or is it C, the driver's actual maximum speed exceeds his ticketed speed? Or is it possible that it's both B and C? Now, lest you think that this is completely fictitious, towns in New Jersey have started using video cameras to record what's going on in traffic. And they'll catch people who are running red lights or speeding through red lights or speeding in general. And they have started to send out tickets in the mail. We got one of these I didn't get it, my wife got it, for running a red light, making illegal right turn on red. Okay, so what say you? How many say A, E-ZPass cannot prove the driver was speeding? Okay, even the state government is not that stupid to just try to extort money out of people. How many say B, E-ZPass cannot prove that the driver can prove that the driver was speeding? Okay, we get a few people. How many say C, the driver's actual maximum speed exceeds his ticketed speed? Okay, so maybe some of you think both of this. Let me go back and say how many think B and might also vote D? How many think? Okay, so how many think C and might also vote D? Okay, so quite a few people think that B is true and C is true, and so you would say D, right? Okay, D is in fact the right answer. Okay, so how is it that E-ZPass can prove that the driver was speeding? Some of you who voted for it, yeah?
Simply just it probably knows where you start, where you got off, and probably estimates how long it would take based on the speed limit zone. So if it was making less time than the speed limit, you would say you're speeding.
Okay, so what does this have to do with the mean value theorem?
That you were exceeding the median for the amount of speed that would be required.
Okay, that's right. So you would get, if you got there in a faster time than it would take if you were driving a legal speed limit, then chances are, well, with a certainty, you have exceeded the legal speed limit. To put it another way, E-ZPass can compute your average speed across the entire interval along which you were driving on the turnpike. And if your average speed exceeds the speed limit, then E-ZPass can invoke the mean value theorem to show that at some point you were driving faster than the speed limit. Does that make sense? Okay. Now, how about C? If we all agree that B is true, why is C also true? Mm-hmm. Mm-hmm. Okay, that's right. So if you're going below your average speed, and I think we can assume that's true unless you're flying through one of these express E-ZPasses, if you drive below your average speed at one point, then you have to drive also above your average speed to catch up to your average. And so your actual maximum speed does exceed your ticketed speed. So if the driver goes to court and says, you can't prove that I drove this fast, then E-ZPass will say, not only can we prove you drove this fast, we can prove you drove faster. So You better be, count yourself lucky that you didn't get a ticket for more. Okay. So like I said, this does not happen in New Jersey, although when I was at Rutgers, I raised this question with a fellow professor, and he said that for that reason, he always takes like rest stops on the turnpike to make sure that EasyPass cannot prove he speeds. That's a little bit paranoid, I think, but maybe you can muse why they don't do this. After all, New Jersey's in a budget crisis. Why don't they just invent this new revenue stream? I'm not looking for a mathematical answer. I'm not sure there is a mathematical answer. Yep? Oh, good. So they would not accept the mean value theorem, and they would still tie up the courts in protesting futilely a theorem that we know is true. Yeah? Oh, and I didn't even think about this. We have trucks going through the state, and if we ticket all of them, then it's going to make delivery costs go up, and those delivery costs will be transferred to the consumer. Okay. Other ideas why this doesn't happen? Yeah? Oh, yes. People would be disincentivized to use EasyPass. Well, that's probably true. I think no matter what, it would end up being unpopular somehow, like very unpopular. You'd have like Wisconsin-level protests in the state capitol. So yes, please cancel our new rail tunnel, but do not make us pay EasyPass fines based on the mean value theorem. No. Okay, so that's my EasyPass question. All right, and very practical, don't you think? Well, next I want to talk about why the mean value theorem is so important to me, and it doesn't seem to be that important when you look at it. And even after I tell you why it's so important, you may not believe it, but I will emote on it at length. So this is one thing we know already. This doesn't necessarily have anything to do with the theorem, but it is true, right? If a function is constant on an interval a to b, then the derivative is 0 on that interval a to b. We all agree on this, right? This was one of the first derivative theorems that we talked about. And you can show it in many different ways. If you're doing it just symbolically, computing the difference quotient, f of x minus f of a over x minus a, if the function's constant, f of x and f of a are going to be the same, and so the difference quotient is going to be 0. Okay, and the limit of 0 would be 0. On the other hand, you can do it sort of geometrically. The tangent line, the derivative is supposed to measure the slope of a tangent line. The graph of a constant function is already a line, so the derivative will be the slope of that line, and a constant function has not a horizontal line. So the derivative will be the slope of a horizontal line, which is already 0. Okay? Or you could play symbolically around with the power rule and think that a constant function can be written as constant times x to the 0. So if you were to take the derivative using the power rule, you get 0 times constant times x to the minus 1, and that would be 0. Okay? This is the least valid of the three arguments, but it's perhaps the most convincing if you love the power rule. Okay. Now, the next question is, what if you have a function and you know that its derivative is 0? Is that function necessarily a constant function? Okay. Now, this is something we also would like to be true. We'd like to, because we can't think of any function that has a derivative of 0 that isn't constant. Oh, no, wait, I can think of one. If you have a step function that looks like this, okay? This is a straight line, a horizontal line, so the derivative would be 0 here. And here is another function whose constant, so its derivative would be 0 as well. So if you put the two together, the derivative is always 0, except at this one place where it's not differentiable. Okay, so that would be one case where you would have a function that wasn't constant, but did have a derivative of 0. But the problem with this is that it's not continuous. If it were continuous and differentiable and had a derivative of 0, then it has to be a constant function. But we don't have any theorem yet that says if you know something about the derivative of a function, you can tell information about that function. All of the theorems that we've been looking at, all of the properties of derivatives, derive from properties of the function. If the function is increasing, the derivative is positive. If the function is decreasing, the derivative is negative. If the function is constant, the derivative is 0. But we haven't yet been able to take information about the derivative and induct from it information about the function. Okay? Until now, we can finally say that if a function has a derivative of 0 all on an interval a to b, then that function is necessarily constant on that interval. Okay, I know. Drum roll, please. This is very exciting. How is that true? Well, let's just take any 2 points, x and y, in the interval a to b. And one of them has to be less, so we'll assume that x is less than y. The function's going to be continuous in between x and y, and differentiable in between x and y as well. Okay, so the mean value theorem says that there's a point, we'll call that point z, in between x and y, such that the average rate of change between x and y is equal to the instantaneous rate of change at z. Okay? But what we know about the derivative tells me that the instantaneous rate of change at z has to be 0. So what we've shown is that the difference quotient, f of y minus f of x over y minus x, has to be 0. And what that means is that the numerator has to be 0. F of y is equal to f of x. Okay? So we just picked any 2 points in between a and b, arbitrary x and y, and we showed that f of y and f of x had to be the same thing. Okay, well that shows that f of y and f of x are the same no matter what 2 points. So, you know, they have to be equal to f of a, they have to be equal to f of b. No matter what, the function values are all the same, so the function has to be constant. Okay? So, if a function has a derivative of 0 and it's differentiable on an open interval, the derivative is 0, tells you that the function is constant. All right. Now, whoop-de-freaking-do. You knew that, right? Or at least you believed it. We can also use this to show that if 2 functions have the same derivative, then they must be different by a constant. Okay, so suppose f and g are 2 differentiable functions on the same open interval a to b, and they have the same derivative, f prime is equal to g prime. Then there's a constant c such that f of x minus g of x is c, or f of x equals g of x plus c. Now this all of a sudden looks a little bit more interesting. 2 functions which have the same derivative must be different by a constant. Okay. Now how is this true? Well, let's just look at f of x minus g of x. Let's just look at f of x minus g of x. That's a differentiable function. And what's the derivative of h of x? I'll just use the difference rule. H prime must be equal to f prime minus g prime. But that would be 0 because f prime and g prime were the same. So what we know now then is that this function, h, has a derivative of 0. And so what kind of function must h be? H must be a constant function. So h of x is a constant, and what that means is that f of x minus g of x is a constant, or equivalently, f of x equals g of x plus a constant. Okay. Now, how many of you have heard of a theorem called the fundamental theorem of calculus? Sounds pretty important, right? Fundamental theorem of calculus. Even if you hadn't heard of it, you'd be impressed by the name alone. Now, you need this property in order to prove the mean value, to prove the fundamental theorem of calculus. You need the mean value theorem in order to prove the fundamental theorem of calculus. And this is why the mean value theorem is the most important theorem, because you need it to prove the fundamental. If you needed to prove the fundamental, it must be even more fundamental than the fundamental theorem of calculus, right? So there you have it. That is why the mean value theorem is the most important theorem of calculus, and yes, that's going to be on the final. No, it probably won't be on the final. I'm not writing the final this year. Okay, so any questions about this property? Okay. The topics today and the questions today are all kind of conceptual in nature, which means that your homework might be more conceptual in nature too, and that might be a little bit strange. But just remember that it's the only theorem that we know of so far which takes information about the derivative of a function and relates it back to the function itself. Okay, so here's another usage of the mean value theorem, which I kind of like. And it's going to take a couple of slides to unfold this story, so please be patient. Let's look at this function here. F of x is defined piecewise, and it's defined to be negative x if x is less than or equal to 0, and x squared if x is greater than or equal to 0. Okay, now the question says, is the function differentiable at 0? But before we get into that, let me ask you, is the function continuous at 0? Is the function continuous at 0? Yes, and why? What's this mean? Are you doing one of these Taylor Swift things? I hope not. Okay. Oh, well, the other ones do. Okay. Why is this function continuous at 0? Well, what is the limit of the function from the left? 0, because, you know, it's from the left we have the function takes the equation negative x, so from the left you get 0. From the right, what's the limit? Also 0, because it looks like x squared, and the limit of x squared is 0. So yes, this function is differentiable at 0, but it's not, yes, this function is continuous at 0, but it's not differentiable at 0. You can picture why by thinking about the graph of this function. Right? The graph of this function, if we do function Simon says, negative x looks like this, right? So negative x for x negative is this branch. And x squared would look like this, but if x is positive, it's just like this. Okay, so the graph of the function looks like this. And here in the center, it's not a smooth curve. It's got this kink in it. And so it's not a differentiable point. Now, you can't do that on the test, right? You can't say, you know, do this, and the function's not differentiable. You would have to go back to the definition. And the definition is in terms of the difference quotient. If you go from the left, f of x is negative x. F of 0 is 0. X minus 0 is x. So from the left, the difference quotient looks like negative x over x, and the limit of that is 1. From the right, the difference quotient looks like x squared over x, and the limit of that is 0. And since the limit of the difference quotient from the left is different from the limit of the difference quotient from the right, then the limit of the difference quotient does not exist, and so the function is not differentiable. That makes sense, right? Since the limit from the left of the difference quotient and the limit of the right from the right of the difference quotient disagree, the function is not differentiable. Okay, well, that's one way to show this, and here's another way to show this. And I say sort of because there's a hidden extra assumption that we're making here. See if you can spot it. One thing you can do is look at the definition of the function on the one side of the interval and the definition of the function on the other side of the interval, and away from that boundary point 0, it's differentiable on the left and it's differentiable on the right. The derivative on the left is the derivative of negative x, which is negative 1. And the derivative on the right is the derivative of x squared, which is 2x. And if you take the limit of negative 1 from the left, you get negative 1. If you take the limit of 2x from the right, you get 0. And since negative 1 and 0 are different, the limit of the derivative does not exist, and so the function is not differentiable at that point 0. Okay. So in this one, we use the definition of the derivative, and we show that the limit of the difference quotient did not exist. And in this one, we said that the limit of the derivative does not exist. And what we seem to be saying is that if the limit of the derivative does not exist at this point, then the derivative cannot exist at that point. And that seems pretty reasonable, because it applies in lots of functions that we look at. But it's actually not true. Okay? Here's the graph of the function, and here's the graph of its derivative. And we can definitely see that the function is not differentiable at 0. But we seem to have said in that sort of solution that the reason it doesn't exist is that the limit of the derivative from the left is different from the limit of the derivative from the right. If you turn that thing around, what you're saying is you're asserting that if a function is differentiable at a point, then the limit of the derivative at that point exists. Or effectively, if the function is differentiable at a point, then the derivative is continuous at that point. And that's not actually true. Yeah, question? Mm-hmm. Oh, yes. So maybe that should be a positive x if the derivative is going to, if the function is going to be this. Yeah. You're right. My graph sucks. I'm just inspired by your T-shirt. That's all. You're correct. I should change that. But the picture also expresses the problem, right? The derivative doesn't have a limit at 0. Is it true then the function cannot be differentiable at 0? Well, actually, it's not true. Here is a function. Nasty function, I do admit, but it has the property that it's differentiable even though the limit of the derivative does not exist at that point. The function takes the definition x squared sine 1 over x. That's not defined for x equals 0, so I'll call it 0 when x equals 0. All right? Now, you can use one of those squeeze theorem arguments to show that the limit of this as x goes to 0 is 0, so the function is continuous. Okay? And if you were to take the derivative away from 0, it's nice and continuous and differentiable. So you can use the product rule, and what you get is that the derivative is 2x times sine 1 over x plus x squared times cosine 1 over x times negative 1 over x squared. Or it simplifies to 2x sine 1 over x minus cosine 1 over x. Okay. Now, the limit as x goes to 0 of this stuff, that's 0 because of the x term, and this is bounded by 1. But here we have cosine of 1 over x. And you remember sine of 1 over x, how it did that wild oscillation thing? Okay, same thing here is going to tell you that the limit of f prime as x goes to 0 does not exist. Okay, so the function's differentiable, though, because you can use the difference quotient, f of x minus f of 0 over x minus 0. That's x squared sine 1 over x minus 0 divided by x minus 0. The quotient is x times sine of 1 over x, and that limit is 0. This goes to 0. This is bounded by 1, so the product goes to 0. So here we have a function. The derivative does not have a limit at 0, but the function is a differentiable at 0. And here's a picture of what's going on. X squared sine 1 over x bounces in between the graph of x squared and minus x squared, and it does this rapid oscillation thing. So it's going up and down and up and down and up and down and up and down and up and down. The closer you get to 0, the faster it goes up and down. And here's the derivative. The closer you get to 0, the more oscillations you're going to get, except at 0, because of this parabola sandwich that's going on here, the derivative ends up being 0, at 0. Okay? But there's no limit of the derivative at 0. Okay, so, why did it work even if it isn't valid? Why is it true that the limit of the derivative did not exist, even though that doesn't mean that the function's not differentiable? Okay, well, maybe I can help us out of this morass that I created. And the way I'll do that is I'll relate information about a function's derivative to information about the limit of that derivative. So here's the lemma. Lemma is a Greek word for a baby theorem. Theorem's also a Greek word, but lemma means small fact. Suppose f is continuous, and the limit of the derivative from the right is equal to a number m. Then the limit of the difference quotient from the right is equal to m. Okay? Our sort of solution took something about the limit of the derivative and asserted something about the limit of the difference quotient. And it turns out you can use the mean value theorem to make that assertion realistic. And here's how you do it. We want to find the limit as x goes to a from the right of f of x minus a over x minus a. Now, f of x minus f of a over x minus a is equal to f prime at some point c, but it's a different c depending on what x is. So I'll call it c sub x. It's some c sub x in between a and x. And as x tends to a, that c sub x is squeezed in between a and x, so it has to go to a too. Okay, so that tells you that the limit as x goes to a of f of x minus f of a over x minus a is equal to the limit as x goes to a of f prime of that number c sub x, whatever it is. But I know that the limit as x goes to a of f prime of x exists and is m. And so the limit of this difference quotient also has to be m. Okay, so if you have the limit of the derivative, you can say that the limit of the difference quotient is the same thing. Okay, now what that means is that if you have a limit of the derivative from the left and a limit of the derivative from the right, then the limit of the difference quotient from the left is the same thing as the limit of the derivative from the left, and the limit of the difference quotient from the right is the same limit of the derivative from the right. And if those two limits are the same, then the function is differentiable. If they're different, then the function is not differentiable. Okay? Does that help us with our sort of solution? Because yes, we show that the limit of the derivative from the right is 0, so the limit of the difference quotient from the right is 0. The limit of the derivative from the left is 1, and so the limit of the difference quotient from the left is negative 1 and negative 1. Okay? And so that's how you actually show it. That's what we just showed. Okay. We show that And here's the proof of what I just said. The limit of the left from the difference quotient is equal to the limit of the left of the derivative. Ditto for the right. If these are the same, then these are the same, so the function is differentiable. If these are different, then these are different, so the function's not differentiable. Okay, so that helps us out of this quandary I created. We are able to not only relate information about the derivative of the function to information about the function, but we can relate information about limits of derivatives of the function to derivatives of the function itself. Okay, so I guess I got too excited about the mean value theorem. I talked too fast. And so I'm pretty much done. What have we learned? We've learned Rolle's theorem. We've learned the mean value theorem, which is equivalent to Rolle's theorem, but a little bit more flexible. And we've learned that a function whose derivative is identically 0 must be constant. And we learned that easy pass is not as bad as we thought because they're not sending us tickets all the time.